Hello there, and welcome to the Physics and Cosmos Academy, a quiet corner for curious minds. Tonight, we're going to tell the full story of the solar system. We'll start in a cold cloud of gas and dust, watch our star burst into life, follow rocks growing into worlds, and even slip under icy crusts to hidden oceans. The city of planets and moons you know today began as a swirling disk of simple stuff. I'm curious, where are you watching from right now? Maybe you're outside looking up at the stars, maybe you're on a bus with headphones, or maybe you're wrapped in a blanket in a quiet room. Tell me in the comments, your place becomes part of our journey. If this feels calm, interesting, or just a nice way to wind down, please tap like and subscribe. It really helps this channel reach others who love gentle, thoughtful science. Now take a slow breath, settle your thoughts, and let's begin our journey into the full story of the solar system. Imagine the story begins in a cold, dark cloud of gas and tiny grains floating in the emptiness of our galaxy. This cloud is mostly hydrogen and helium left from older stars, with tiny amounts of heavier elements. Over millions of years, disturbances like shockwaves from nearby exploding stars compress parts of this cloud. Gravity begins to pull the gas and dust into a tighter space. As more material gathers, the cloud's center grows denser and hotter. The entire cloud starts to spin. Because of the way angular momentum works, spinning speeds up as the cloud shrinks, much like an ice skater pulling in their arms. The cloud flattens into a broad, thin disk with a bulge in the center. This disk is called a protoplanetary disk. Within this spinning disk, microscopic dust grains bump into one another and stick together. At first, it's static electricity and gentle sticking that hold them. As they grow bigger, gravity takes over, pulling clumps together into larger and larger bodies. Pebbles become boulders, boulders become mountain-sized chunks, and these become the building blocks of planets called planetesimals. Collisions are frequent, some are gentle and some are violent. When bodies smash together, they sometimes break apart, but often they merge, melting and mixing. In the inner part of the disk, where it is hot, only materials like silicates and metals can condense into solids. In the cooler outer regions, ices of water, ammonia and methane can freeze out as well, so bodies there grow larger more quickly. As the largest embryos continue to sweep up material, they begin to clear their orbits of smaller debris. In the outer disk, the growing planetary embryos become big enough to pull in thick envelopes of gas. This is how giant planets like Jupiter and Saturn form, with huge atmospheres made mostly of hydrogen and helium. In the inner disk, fewer light gases are available, so the embryos remain as rocky bodies. The layout of the early solar system is not fixed. Scientists think the young giant planets moved around, pulling on each other and on smaller bodies. One model suggests that Jupiter moved inward toward the region of Mars before moving outward again, shaping where the smaller planets ended up. Farther out, gravitational interactions among the giant planets and the leftover disk of planetesimals may have sent a shower of comets and asteroids into the inner solar system in what is called the Late Heavy Bombardment. At the center of the disk, gas and dust kept falling inward. Pressure and temperature rose until nuclear fusion started. The newborn sun lit up, sending light and a steady stream of charged particles called the solar wind out into space. This strong wind blew away much of the leftover gas and dust, leaving behind the newly formed planets and countless smaller bodies. What remains today are the 8 major planets, many moons and belts of asteroids and comets, all part of the family that was born from that original cloud. Evidence for this story comes from many clues. Meteorites, which are fragments of ancient asteroids that fall to Earth, contain little round beads called chondrules and bits of calcium-aluminum-rich inclusions. These are some of the oldest solids in our solar system, and their chemistry preserves the conditions of the early disk. Some meteorites contain tiny mineral grains older than the Sun itself, telling us that material from earlier stars was incorporated. Astronomers also observe young stars surrounded by dusty disks in other parts of our galaxy, with gaps and rings carved by planets that are still forming. These observations show that the process of building planets from disks is common. The way planets are arranged today reflects the physical conditions of that early disk. Mercury, Venus, Earth and Mars are small and rocky because they formed in the inner region where it was too hot for ices to survive. The gas giants formed further out where ices could condense and add mass quickly. Uranus and Neptune are called ice giants because much of their interiors are water, ammonia and methane ices trapped under thick atmospheres. Beyond Neptune, a broad belt of icy bodies called the Kuiper belt marks the outer edge of the original disk, while a distant cloud of comets called the Oort cloud may stretch halfway to the nearest star. As planets grew, their interiors heated up. Radioactive elements and collisions melted the young bodies. Heavy metals like iron and nickel sank to the center, forming cores, while lighter silicate rocks floated up to make mantles and crusts. Some bodies differentiated completely into layers, while others remained a mix of rock and metal. The early Earth likely experienced a period of global magma ocean. Outgassing from molten rock released water vapor, carbon dioxide and other gases to form a primitive atmosphere. Many of the volatiles on Earth, including a significant portion of its water, probably arrived from asteroids and comets that bombarded the planet during its youth. The early solar system was a violent place, with constant impacts shaping young worlds. The scars of this era are still visible today on the surfaces of Mercury, the Moon, and many moons of the outer planets, which are covered in craters. On Earth, plate tectonics, weathering and life have erased most of the early craters, but a few ancient impact sites remain. Understanding this period helps us appreciate not only how our own planetary neighborhood formed, but also the likely formation histories of the thousands of planetary systems discovered around other stars. To truly understand our planetary family, we have to understand its parent star. The Sun is a glowing ball of mostly hydrogen gas held together by its own gravity. It makes up more than 99% of all the mass in the solar system, and its gravity dominates the motions of all planets and smaller bodies. If you could look inside, you would find layers defined by how energy moves. At the very center is the core. Here, temperature and pressure are so immense that hydrogen atoms fuse into helium. This process, called nuclear fusion, releases an enormous amount of energy. Every second, the Sun turns millions of tons of hydrogen into helium and shines the equivalent of trillions of atomic bombs. The energy released as gamma rays diffuses outward through the radiative zone. In this deep region, photons are absorbed and re-emitted countless times, taking thousands to millions of years to reach the next layer. Further out is the convective zone. Here, material is cooler and forms circulating cells. Hot plasma rises toward the surface, cools and sinks again, transferring heat in giant bubbles. This boiling motion creates the granular texture we see on the solar surface. The visible surface of the Sun is called the photosphere. Above it lies the chromosphere and the corona, the outer atmosphere, which extends millions of kilometers into space. The Sun is not a featureless sphere. Magnetic fields generated by moving charged particles create complex patterns. Sunspots are dark, cooler regions associated with concentrated magnetic fields. They appear in cycles roughly every 11 years, when the number of spots waxes and wanes. Magnetic fields sometimes snap and reconnect, releasing bursts of energy known as solar flares. Large clouds of plasma can also be blown into space as coronal mass ejections. When these streams of charged particles reach Earth, they can disturb our magnetic field, cause auroras and sometimes disrupt satellites and power grids. The Sun constantly emits a flow of charged particles called the solar wind. This wind streams out through the solar system at speeds of hundreds of kilometers per second. It shapes the environment around each planet and helps sculpt the tails of comets. At the edge of the solar system, the solar wind meets the interstellar medium in a boundary called the heliopause. In addition to light and heat, the Sun provides the gravitational anchor that keeps planets and smaller bodies in orbit. Because it is so massive, even distant objects in the Oort cloud feel its pull. The The Sun's gravity and radiation also influence the shape and behavior of planetary atmospheres. On Earth, sunlight powers photosynthesis, drives weather and ultimately enables life. Without the Sun's constant energy output, Earth would quickly freeze into an uninhabitable ice ball. The Sun is middle-aged in stellar terms, having burned for about 4.6 billion years. It has fused about half of its hydrogen in the core. Over time, the Sun will slowly grow brighter and larger. In billions of years, it will expand into a red giant, engulfing Mercury and possibly Venus. Eventually, it will shed its outer layers and end its life as a white dwarf surrounded by a glowing planetary nebula. Knowing this future reminds us that stars and planetary systems have finite lifetimes. Our modern-day civilization thrives in the relatively quiet, stable period of solar life, a cosmic middle age that has allowed complex life to evolve and flourish. Scientists study the Sun with a fleet of telescopes and spacecraft. Instruments like SOHO, SDO, and Parker Solar Probe monitor its activity up close, capturing high-resolution images of flares and measuring the solar wind. Helioseismology, which examines sound waves traveling through the Sun, allows researchers to map its interior. Neutrinos, ghostly particles produced by fusion in the core, pass through matter almost undisturbed and provide direct evidence of nuclear reactions deep inside. Understanding our star is not only a scientific endeavor, but also practical, since space weather affects modern technologies such as communications and electrical grids. The Sun rotates, but not like a solid body. Because it is made of gas and plasma, different parts of the Sun rotate at different speeds. The equator completes a rotation in about 25 days, while regions near the poles take over 30 days. This differential rotation twists magnetic field lines and contributes to the 11-year sunspot cycle. Over an entire 22-year magnetic cycle, the Sun's magnetic poles flip and return to their original orientation. The outer atmosphere, or corona, is much hotter than the surface below it. While the photosphere is about 5,500 degrees Celsius, the corona reaches temperatures of millions of degrees. The exact mechanism heating the corona is an active area of research, but it likely involves magnetic waves and reconnection events that transfer energy upwards. The corona is visible to the naked eye during total solar eclipses as a pearly white halo. It is also the region where the solar wind originates. Despite being an average star, the Sun holds many mysteries. One puzzle, known as the faint young sun problem, asks how early Earth stayed warm enough for liquid water when models suggest the young Sun was about 30% fainter than it is today. Possible explanations involve higher levels of greenhouse gases or lower planetary albedo in the early atmosphere. Whatever the solution, it underscores the delicate balance between solar output and planetary conditions needed for habitability. Measurements of the Sun are tied to human activities. The way we measure time and define units like the year rely on Earth's orbit around the Sun. Observations of the Sun's movement through the sky were crucial for ancient calendars and agriculture. Solar orientation influenced architecture and rituals across cultures. Solar eclipses were once seen as omens. Now they are opportunities for scientists to study the corona. As our reliance on satellites, power grids, and electronics grows, understanding and forecasting solar storms becomes increasingly important. The distance between Earth and the Sun averages about 150 million kilometers, a span defined as an astronomical unit. Light takes about 8 minutes to travel this distance, meaning we always see the Sun as it was 8 minutes ago. The solar energy that reaches the top of Earth's atmosphere is called the solar constant and amounts to about 1,160 watts per square meter. Our atmosphere and oceans absorb, reflect, and redistribute this energy, driving weather and climate. Only a tiny fraction of the Sun's total output ever reaches Earth, but it is enough to make our planet vibrant. Even at Pluto's distance, roughly 40 times farther than Earth, the Sun still appears as a bright star and provides enough warmth to cause seasonal changes. In every sense, the Sun is the engine of our solar system. It set the stage for planet formation, shapes the environment in which planets and moons evolve, and sustains life on Earth. It is a typical star in some ways, yet to us it is unique, our personal star, the source of nearly all the energy that feeds our world. Our documentary will use our star not just as a scientific topic, but as a character whose life story is intertwined with the fates of the planets. The Sun's light warms, its wind sculpts, and its gravity binds. It is both a nurturing parent and a sometimes unpredictable actor, shaping the environment where life emerged. The inner worlds, Mercury, Venus, Earth, Mars, 4 small rocky planets circle close to the Sun. They are called the terrestrial planets because, like Earth, they have solid surfaces. Yet each is a distinct world with its own story. Mercury is the smallest and innermost planet. It orbits the Sun in just 88 days. From far away it looks like our moon, grey, pocked with craters, and lacking any visible atmosphere. This similarity is not coincidence. Mercury has no substantial atmosphere to protect its surface from constant meteorite bombardment or to moderate its temperature. It has a huge iron core that makes up most of its volume, surrounded by a thin layer of rock. Scientists think Mercury may have lost much of its outer layers in a giant impact early in its history, or perhaps it formed from metal-rich material. Because it rotates slowly and lacks an atmosphere, temperatures on Mercury swing dramatically, scorching hot during the long day and freezing cold at night. Its surface hosts cliffs hundreds of kilometers long called scarps, created as its core cooled and the planet shrank. Spacecraft like Mariner 10 and Messenger have shown us detailed images of basins and strange hollow depressions that suggest Mercury still releases volatile gases. Venus, the second planet, is similar in size to Earth and is sometimes called our sister planet. But the resemblance is deceptive. A thick, toxic atmosphere made mostly of carbon dioxide blankets the planet, trapping heat in an extreme greenhouse effect. The surface temperature is hot enough to melt lead, and the pressure at the ground is over 90 times that on Earth, similar to being deep in an ocean. Sulfuric acid clouds shroud the planet, reflecting sunlight and giving Venus a brilliant appearance in our dawn and dusk skies. Radar images taken through the clouds reveal a landscape of broad plains, highland regions, and thousands of volcanoes, many of which appear relatively young. Venus rotates very slowly and in the opposite direction of most planets. One day on Venus, the time it takes to spin once, is longer than its year, the time it takes to orbit the Sun. There is no evidence of plate tectonics like on Earth. Instead, heat may be released through periodic resurfacing events where lava floods the surface. Although it likely formed with similar ingredients as Earth, Venus lost its water. Ultraviolet light from the Sun broke apart water molecules, and the lighter hydrogen escaped to space. Without water, carbon dioxide accumulated, leading to a runaway greenhouse that transformed the planet into the inhospitable world we see today. Earth is the third planet, and the only place we know that harbors life. It sits in the so-called habitable zone, where temperatures allow liquid water to exist on the surface. Water covers more than 2/3 of our planet, forming oceans that moderate climate and create a home for countless organisms. The atmosphere is a mix of nitrogen, oxygen, and trace gases that together make Earth comfortable for living things. Oxygen in our air comes from billions of years of photosynthesis by plants and microbes. Carbon dioxide and water vapor provide a natural greenhouse effect that warms Earth just enough. Earth's interior remains geologically active. Heat from the core drives plate tectonics, where rigid plates of crust float on the slowly convecting mantle. Plates move, collide, and pull apart, building mountains, opening oceans, and recycling crust. This activity helps regulate the climate by cycling carbon between the atmosphere, oceans, and rocks. Volcanoes release gases from the interior, and earthquakes remind us that the planet is alive inside. The magnetic field generated by the rotating, convecting metal in the core shields the planet from solar wind and cosmic radiation. Without this field, our atmosphere might have been stripped away, as appears to have happened on Mars. Earth's environment has changed dramatically over time, from a molten surface to the formation of continents, from an oxygen-poor atmosphere to one rich in oxygen. Life has played a major role in shaping the atmosphere and surface, and in turn the changing environment has driven evolution. Earth's moon, formed from a colossal impact, orbits at an average distance of about 384,000 kilometers and tidally interacts with Earth. Its gravitational pull raises tides in the oceans, which influence coastal ecosystems and may have aided the transition of life from sea to land. The moon also stabilizes Earth's tilt, preventing extreme swings in climate. Mars, the fourth planet, is a cold desert world. Once, billions of years ago, liquid water flowed across its surface. Orbital images show dry river channels, deltas, and lake beds. Rovers have found evidence of ancient mineral deposits that form in water, such as clays and sulfates. Mars likely had a thicker atmosphere and a magnetic field early in its history, which would have allowed water to remain stable on the surface. Over time, the planet cooled and its core solidified, weakening its magnetic field. The solar wind stripped away much of the atmosphere, and the surface water either froze or evaporated. Today, the atmosphere is thin and mostly carbon dioxide. It is so thin that liquid water quickly boils or freezes. Temperatures are generally below freezing, though midday temperatures at the equator can be comfortable. Dust covers much of the surface, and storms can envelop the planet for weeks. Mars has the tallest volcano in the solar system, Olympus Mons, rising 3 times the height of Mount Everest. It also boasts Valles Marineris, a canyon system that dwarfs Earth's Grand Canyon. The planet's polar regions have caps of water ice and dry ice, frozen carbon dioxide, that wax and wane with the seasons. Rovers like Spirit, Opportunity, Curiosity, and Perseverance, and orbiters from many nations, have dramatically expanded our knowledge of Mars, searching for signs of past or present life, and preparing for future human exploration. For all their differences, the inner planets share some common themes. Each has experienced bombardment by asteroids and comets, leaving craters of all sizes. Each has seen volcanism shape its surface, though the types of volcanoes and the sources of melt differ. Each has undergone internal differentiation, with dense metals sinking to the core and lighter silicates rising. Yet the amount of internal heat left over from formation determines whether a planet remains geologically active. Mercury's small size means it lost heat quickly. While there is evidence of ancient volcanism, today it is geologically quiet. Venus and Earth, similar in size, have retained more heat. Venus lacks the large-scale plate tectonics that move Earth's continents, but its surface shows signs of lava flows and possible periodic resurfacing. Earth is unique in having separate plates that grind together, creating earthquakes, mountains, and ocean trenches. Mars, intermediate in size, cooled but still retains some internal heat. Evidence of recent volcanic activity exists but is sparse. Its crust is a single plate. Mercury's orbit is elliptical, taking it as close as 46 million kilometers and as far as 70 million kilometers from the Sun. It spins 3 times every 2 orbits, leading to a 3-to-2 resonance. A day-night cycle on Mercury, from sunrise to sunrise, lasts 176 Earth days, so the same side faces the Sun every other orbit. Radar observations have detected water ice in craters near Mercury's poles, where deep shadows never see sunlight. Cometary impacts likely delivered this ice. The Bepicolombo mission, launched by Europe and Japan, is on its way to Mercury to further study its composition, magnetic field, and environment. Venus is a world of paradoxes. Its thick clouds hide the surface, making direct observation difficult. The atmosphere circulates much faster than the solid planet rotates, a phenomenon known as superrotation. Winds in the cloud tops race around the planet in about 4 Earth days. The dense carbon dioxide atmosphere allows only a little sunlight to reach the surface. Most light is absorbed or scattered by clouds and absorbed by the thick air, contributing to the extreme heat. Spacecraft have survived on the surface for only short periods before succumbing to the high temperature and pressure. Nevertheless, exploration continues, and scientists speculate that microbial life may once have existed when the planet was younger and cooler. Recent observations hint at possible active volcanoes and transient atmospheric gases, but these remain subjects of debate. Earth's story is intimately tied to life. The presence of liquid water, a protective magnetic field, and a stable climate allowed life to emerge. Life then altered the planet. Cyanobacteria in the oceans began producing oxygen through photosynthesis billions of years ago. This oxygen gradually built up in the atmosphere, leading to the great oxygenation event that transformed the environment and allowed more complex life to evolve. Continents drifted, collided and broke apart, driving changes in climate and ecosystems. Ice ages came and went. Human activity has now become a geological force, changing the composition of the atmosphere and impacting climate. While this documentary focuses on the larger cosmic story, it reminds us that our planet's environment is not static and that our actions can influence it. Mars remains a subject of fascination. Its thin atmosphere offers little protection from radiation and little insulation. Without a global magnetic field, the solar wind interacts directly with its upper atmosphere, stripping away gas molecules. NASA's MAVEN orbiter measures this escape, helping scientists understand how Mars lost most of its air. Some water remains locked up as ice in polar caps and in the ground, and small amounts of water vapor are present in the atmosphere. Landers have detected frost and seasonal flows of briny water on slopes. The possibility of underground aquifers or briny lakes remains open. Scientists speculate that microbial life might survive underground, where heat and liquid water may exist. Missions like the ExoMars rover and future sample return missions aim to search for biosignatures. By exploring these 4 worlds, we gain insight into how planets respond to different conditions. They teach us about the processes that shape solid planets and the factors that make a world habitable. We can then look at planets around other stars and imagine what they might be like. Earth and its moon share a history that began with a catastrophe. The early solar system was a chaotic place, full of collisions. Our planet itself grew by merging with countless smaller bodies. One of the last and largest of these collisions shaped Earth forever. According to the leading hypothesis, a Mars-sized body often called Theia struck the still-forming Earth about 4.5 billion years ago. The impact was not a glancing blow nor a head-on smash, but somewhere in between. Theia's metallic core merged with Earth's core, adding mass and heat. The outer layers of both bodies were vaporized and flung into orbit around Earth, forming a ring of molten rock and debris. Over a short time, perhaps only months or years, this material clumped together and coalesced into a single body, the Moon. Evidence for this scenario comes from the Moon's composition. Lunar rocks collected by Apollo astronauts and meteorites from the Moon have chemical compositions very similar to Earth's mantle. Yet the Moon has a much smaller iron core relative to its size. If the Moon formed largely from Earth's outer layers and Theia's outer material, this makes sense. Computer simulations reproduce the conditions needed to create a Moon with the right mass and composition. Alternative ideas, such as capture or co-formation, struggle to account for all the data. the impact had several consequences. First, it delivered additional energy to Earth, melting much of the crust and creating a global ocean of magma. This melt took millions of years to cool and solidify. Second, it set the rotation of Earth. Before the impact, Earth may have been spinning faster or slower, with a different tilt. The collision likely increased Earth's rotation rate, shortening the day and tilted its axis. Today, Earth's axis is inclined about 23.5 degrees relative to the plane of its orbit. This tilt gives us seasons. Without the Moon, Earth's tilt might have been unstable, wobbling over a wide range due to gravitational interactions with other planets. Computer models show that the Moon acts like a stabilizing weight, keeping Earth's spin axis relatively steady. This stability has been important for maintaining a climate that is favorable to life over long periods. Third, the Moon's gravity raises tides on Earth. Tides are not just waves at the beach, they are bulges in the oceans, and to a lesser extent in the crust, that follow the Moon as it orbits. Because Earth rotates faster than the Moon orbits, the tidal bulge is slightly ahead of the Moon's position. The gravitational interaction between the bulge and the Moon transfers energy, causing Earth's rotation to slow and the Moon's orbit to expand. As a result, the length of Earth's day has gradually increased over billions of years, and the Moon now moves away from Earth at a rate of about 3.8 centimeters per year. In the distant past, days were shorter, and there were more of them in a year. Fossil corals and rhythmites, tidal sediment deposits, preserve evidence of these changes. Tides also create tidal zones along coastlines that are rich in nutrients and host a variety of life forms. Some scientists believe that tidal pools may have provided stable environments for the origin of life on land. The interplay of Earth and Moon goes beyond tides and axial stability. The Moon moderates the effects of impacts. Early in the solar system, our planet and its companion were bombarded by asteroids and comets. Many of the craters on the Moon date from a period known as the Late Heavy Bombardment, a time when the gravitational movements of the giant planets may have sent a rain of debris into the inner solar system. Earth's larger gravity attracted more impactors, but erosion and tectonics have erased most traces. On the Moon, without air or water, craters remain as a record of those violent days. The bombardment may have delivered water and organic molecules to Earth, essential ingredients for life. Some impacts also created deep-sea hydrothermal systems that could have been habitats for early life. The early Moon may have had an atmosphere created by volcanic eruptions and by vaporized rock after the giant impact. But the Moon cooled quickly. Its small size meant it lost heat faster than Earth. Volcanic activity gradually subsided and its atmosphere escaped into space. Today, the Moon has only a very tenuous exosphere. Micrometeorite impacts and the solar wind continuously bombard its surface. The dark basaltic plains we see as the lunar seas are ancient lava flows, dating back billions of years. The highlands are older crust, heavily cratered. There is evidence of water ice in permanently shadowed craters at the lunar poles. This ice may be resources for future exploration. The story of Earth and Moon is also a human story. For millennia, the Moon has been a guide for timekeeping, inspiring myths, and measuring the months. Its phases result from our changing view of the half-lit sphere as it orbits Earth every 27.3 days. Eclipses occur when the Sun, Earth, and Moon align, with lunar eclipses turning the Moon a deep red as it passes through Earth's shadow. The first human footsteps beyond Earth took place on the Moon in 1969. Astronauts explored the lunar surface, collected samples, and installed instruments. These missions revolutionized our understanding of the Moon's history and composition. Future missions plan to establish a long-term presence on or near the Moon, using it as a testing ground for exploration of Mars and beyond. After the giant impact, molten rock covered Earth. Over time, the planet cooled. Water vapor in the atmosphere condensed and rained out, creating oceans. Carbon dioxide dissolved in the water or was locked in rocks. Volcanic activity continued, releasing gases and building land masses. The crust solidified, forming protocontinents that later merged and split as plate tectonics began. The presence of a large moon created strong tides that stirred the oceans, mixing chemicals and perhaps playing a role in the chemistry that led to life. Daylight and darkness were shorter then, meaning the cycle of heating and cooling on the surface was rapid. Early Earth's atmosphere lacked oxygen. It likely contained nitrogen, carbon dioxide, water vapor, methane, and ammonia. As the planet cooled, conditions stabilized enough for life to emerge. Cyanobacteria evolved the ability to perform oxygenic photosynthesis, releasing oxygen as a waste product. Oxygen gradually accumulated, altering the atmosphere and ocean chemistry. This change allowed for the development of aerobic respiration and eventually complex organisms. The moon was a silent witness to all these transitions. The moon has influenced cultural and biological rhythms. Many organisms, from corals to certain worms, spawn according to lunar cycles. Farmers have long used lunar phases to guide planting and harvesting. Poets and artists have drawn inspiration from the glowing orb in the night sky. The predictability of lunar phases provided ancient peoples with a reliable calendar. The word month comes from the moon. Understanding its motion allowed early astronomers to develop sophisticated models of celestial mechanics. Modern lunar science builds on a wealth of data. Lunar Prospector, Kaguya, Chandrayaan-1, and NASA's Lunar Reconnaissance Orbiter have mapped the surface in high resolution, measured gravity variations, and searched for water. The Chinese Chang'e missions have landed rovers and brought back samples. All these missions reveal a complex history recorded in the lunar rocks. By studying isotopes, scientists can date lunar events and refine our understanding of when and how the moon formed. The presence of water ice in permanently shadowed polar regions is particularly exciting, as it could support future human activity. Extracting water would provide drinking water, breathable oxygen, and even rocket fuel. Looking to the future, the Earth-Moon partnership continues to evolve. International plans for a lunar gateway station and surface bases intend to use the moon as a stepping stone for missions deeper into the solar system. The gravitational environment on the moon is only 1/6 of Earth's, offering a unique environment for studying biology and materials. Lunar resources could support manufacturing and fuel production. The moon's far side, shielded from Earth's radio noise, is a potential site for radio telescopes probing the early universe. In the grand scheme of things, the Earth and Moon are inseparable. Their formation is one of the most dramatic events in the history of our planet. The Moon's presence has moderated Earth's climate and length of day, influencing the environment in which life evolved. Its phases have inspired culture, its tides have shaped coasts, and its surface holds a record of solar system history. As we tell the story of our solar system, the Earth-Moon pair stands out as an example of how violent beginnings can lead to a balanced and life-friendly system. In addition to the 8 major planets and their moons, the solar system contains countless smaller bodies. These asteroids, comets, meteoroids, and dust particles are the leftovers from planet formation. They preserve clues about the early solar system and continue to play an important role today. Asteroids are rocky or metallic bodies that orbit the Sun. Most reside in the main asteroid belt between Mars and Jupiter. The gravitational influence of Jupiter prevented these objects from coalescing into a planet. Instead, they remain as a swarm of bodies ranging from tiny pebbles to dwarf planet Ceres, which is nearly 1,000 kilometers across. Asteroids come in different types based on their composition. C-type, carbonaceous asteroids are dark and rich in carbon and volatile compounds. They are thought to be similar to the material that formed the outer part of the inner solar system and may have delivered water and organic molecules to Earth. S-type, silicaceous asteroids are made mostly of silicate rock and metals and dominate the inner asteroid belt. M-type asteroids are rich in metals like iron and nickel and may be remnants of the cores of differentiated planetesimals that were shattered by impacts. Farther out, beyond Neptune, lies another belt of bodies called the Kuiper belt. These objects are icy and include dwarf planets like Pluto, Eris, Haumea, and Makemake. Comets that we see with long tails often come from this region when gravitational nudges send them toward the inner solar system. Even farther away, at the edge of the Sun's gravitational influence, is the hypothetical Oort cloud, a spherical shell of trillions of icy bodies. Comets from the Oort cloud visit the inner solar system only rarely, on timescales of thousands to millions of years. Comets are often called dirty snowballs. They consist of frozen water, carbon dioxide, ammonia, and other volatiles mixed with dust and rocky material. When a comet approaches the Sun, solar heat warms the surface, causing the ices to sublimate, turn directly from solid to gas. This gas and dust form a glowing coma around the nucleus. Solar radiation and the solar wind push the gas and dust away, creating tails that can stretch millions of kilometers. One tail, made of ions, points directly away from the Sun due to the solar wind. The other tail, made of dust, curves gently along the comet's orbit. Comets are time capsules. They formed in the cold outer regions of the solar nebula and have been preserved for billions of years. Studying them helps scientists understand the composition of the early solar system. When small fragments of asteroids or comets enter Earth's atmosphere, they are called meteoroids. As they streak through the atmosphere, they heat up and glow, creating meteors or shooting stars. Most meteoroids burn up before reaching the ground. Those that survive to reach the surface are called meteorites. Iron meteorites come from the cores of ancient planetesimals. Stony meteorites come from their crusts or mantles, and stony iron meteorites contain a mixture of both. By studying meteorites, scientists learn about the building blocks of planets. Some carbon-rich meteorites contain amino acids and other organic molecules, suggesting that life's ingredients were available early on and may have been delivered to the young Earth by asteroids and comets. Small bodies have shaped Earth's history in dramatic ways. A large asteroid impact is widely believed to have caused the mass extinction that wiped out the dinosaurs 66 million years ago. The impact created a crater over 150 kilometers wide on the Yucatan Peninsula. Dust and aerosols thrown into the atmosphere blocked sunlight, causing climate cooling and collapse of ecosystems. Throughout Earth's history, impacts have been agents of both destruction and renewal. They can cause mass extinctions, but also deliver water, organics, and minerals that are essential to life. Understanding these objects is thus critical not only for science but for protecting our planet. Planetary defense is the effort to identify and mitigate potential impacts from near-Earth objects, NEOs. NEOs include asteroids and comets with orbits that bring them close to Earth. Organizations around the world use ground-based and space-based telescopes to find, track, and characterize these objects. Once an NEO is found, astronomers compute its orbit and predict its future positions. The goal is to identify any object that might pose a threat years in advance. If a hazardous object were discovered, there are strategies to deflect it. One method is the kinetic impactor. A spacecraft deliberately collides with the asteroid at high speed to slightly change its velocity and, over time, its trajectory. Another idea involves using a spacecraft's gravity to tow the asteroid, known as a gravity tractor. More speculative methods include using concentrated sunlight to vaporize material from the asteroid's surface, producing jets that push it off course. In 2022, the Double Asteroid Redirection Test (DART) mission demonstrated the kinetic impactor technique for the first time. The mission targeted a binary asteroid system called Didymos and its smaller moon Dimorphos. DART slammed into Dimorphos at over 20,000 kilometers per hour, altering its orbit around Didymos by a significant amount. This test showed that it is possible to change the trajectory of a small asteroid using a spacecraft. A follow-up mission by the European Space Agency called Vera will return to the system to measure the crater and understand the internal structure of the asteroid. Other missions like NASA's OSIRIS-REx and Japan's Hayabusa have visited asteroids, collected samples and brought them back to Earth. These missions provide invaluable information about asteroid composition and structure, which is essential for designing effective deflection strategies. Comets are also monitored for potential hazards. Their long, unpredictable orbits and activity make them more difficult to track. However, most comets that cross Earth's path are discovered well in advance. Historically, comets were seen as omens. Today, they are targets of scientific study and potential threats. Missions like ESA's Rosetta, which orbited Comet 67P Churyumov-Gerasimenko and landed a probe on its surface, have revealed that comets have complex, organic-rich surfaces with cliffs, pits and jets. Such missions transform our understanding of these ancient bodies. Small bodies are also resources. Some asteroids are rich in metals that could be used for construction in space. Others contain water that can be split into hydrogen and oxygen for rocket fuel. Companies and space agencies are exploring the possibility of asteroid mining. Before such activities become practical, it is essential to understand the ethical and legal frameworks to ensure that resources are used responsibly and that scientific study is not compromised. There is a romantic side to small bodies as well. Every year, when Earth passes through the debris trail of a comet, we see a meteor shower. The Perseids, Leonids and Geminids are examples. Families gather to watch the night sky light up with streaks of light. These events remind us that we are part of a dynamic cosmic environment. The shooting stars we wish upon are tiny fragments of comets burning up as they enter our atmosphere. Within the asteroid belt, certain regions are largely empty. These gaps, known as Kirkwood gaps, correspond to orbital resonances with Jupiter. When an asteroid's orbital period is a simple fraction of Jupiter's period, Jupiter's regular gravitational tugs can nudge the asteroid into a new orbit. Some asteroids leave the main belt and become near-Earth asteroids. Others become Trojan asteroids, which share an orbit with a planet. Jupiter has thousands of Trojan asteroids clustered around points that lead and follow it in its orbit. Neptune and even Mars have smaller Trojan populations. Studying these groups helps scientists understand how the planets migrated and captured bodies in their gravitational wells. Dwarf Planet Ceres, the largest object in the asteroid belt, blurs the line between asteroids and planets. Ceres is spherical, indicating that its gravity has pulled it into hydrostatic equilibrium. The Dawn spacecraft orbited Ceres and found evidence of water-rich minerals, bright spots of salt left by briny water seeping onto the surface, and possible cryovolcanism. These discoveries suggest that even in the dry asteroid belt, there may be subsurface water. Another interesting body, Vesta, shows signs of past volcanism and a differentiated interior. Meteorites from Vesta have been identified on Earth, linking laboratory samples to a specific body. Beyond the asteroid belt, the Centaurs orbit between the giant planets. These icy, comet-like bodies are thought to originate in the Kuiper belt and have been scattered inward. They have unstable orbits and can become short-period comets. Some of these Centaurs, like Chiron and Chariklo, have been observed to have rings, making them miniature analogues of the giant planets. Such discoveries highlight the diversity of small bodies. The influence of non-gravitational forces is also important for asteroids. The Yarkovsky effect occurs when an asteroid absorbs sunlight and re-emits energy as heat, providing a tiny thrust that can alter its orbit over millions of years. This effect depends on the asteroid's rotation, shape, and surface properties. Understanding it is crucial for predicting asteroid paths far into the future. The Yorp effect, named for Yarkovsky, O'Keefe, Radzievsky, and Paddock, can change an asteroid's rotation rate and axis orientation due to sunlight reflecting and radiating away from irregular surfaces. These subtle effects can cause an asteroid to spin faster and in some cases break apart. Planetary defense also involves coordinated international efforts. NASA's Planetary Defense Coordination Office works with agencies worldwide to detect, track, and characterize hazardous objects. The International Asteroid Warning Network shares data among observatories. Space agencies plan reconnaissance missions to potential hazard objects to understand their structure and surface properties. Planning for such missions years or decades in advance is essential because small changes to an asteroid's orbit can prevent an impact if applied early enough. In addition to deflection, emergency response plans consider evacuation or shelter-in-place scenarios if a small asteroid were discovered with insufficient warning. Education and public outreach help ensure that people understand the real risks without giving in to sensationalism. Our own planet is not alone in facing impacts. The pockmarked surfaces of the Moon, Mars, Mercury, and many moons of the outer planets bear witness to the constant rain of debris. Jupiter, with its strong gravity, sometimes acts as a shield, pulling in comets and asteroids that might otherwise threaten inner planets. At the same time, its gravitational perturbations can send smaller bodies inward. They are both sculptors and guardians, shaping the architecture of the solar system. In exploring the small bodies of our solar system, we are learning about the materials and conditions from which our world formed. These bodies are keys to understanding the distribution of water and organic molecules that set the stage for life on Earth. They are natural laboratories for studying the chemistry that occurs in cold, dark environments. They are potential sources of raw materials for future explorers. And they are a constant reminder that our planet, beautiful and life-filled, travels through a cosmos filled with both potential threats and invaluable clues about our origins. The two largest planets in our solar system, Jupiter and Saturn, are gas giants. They are mostly hydrogen and helium, the same elements that make up the Sun, but they never became large enough for nuclear fusion to ignite. Their immense masses, Jupiter alone is more massive than all the other planets combined, make them powerful players in the story of the solar system. Jupiter formed early, probably within the first few million years. As the young Sun cleared out the remaining gas, Jupiter's core grew large enough to pull in a vast envelope of hydrogen and helium. Saturn followed, forming slightly later and further out. Because gas was abundant early on, these giants could become huge before the solar wind stripped away the remaining material. Their formation influenced the orbits of smaller bodies. Jupiter's gravity likely kept the asteroid belt from turning into a planet and may have flung icy bodies toward the inner solar system, delivering water to Earth. Jupiter's diameter is over 11 times that of Earth, and its mass is more than 300 times greater. Yet it is mostly fluid. Beneath its colorful cloud tops, hydrogen exists as a gas, then as a liquid, and under extreme pressure as metallic hydrogen. Metallic hydrogen is a state of matter where electrons are free to move, making it an excellent conductor of electricity. Deep in Jupiter's interior, this metallic hydrogen, combined with rapid rotation, one rotation every 9 hours and 56 minutes, generates a powerful magnetic field. Jupiter's magnetosphere extends millions of kilometers into space. Charged particles trapped in this field create intense radiation belts that would be lethal to unprotected spacecraft. Jupiter also emits strong radio signals and has brilliant auroras at its poles. Saturn is slightly smaller and less massive than Jupiter, with a diameter about 9 times that of Earth and a mass about 95 times Earth's. Its average density is less than that of water, meaning that if you could find an ocean big enough, Saturn would float. Saturn's interior also contains metallic hydrogen, though perhaps less than Jupiter. Saturn rotates once in about 10 hours and 34 minutes, generating a strong magnetic field that is nearly aligned with its rotation axis. This alignment makes Saturn's magnetic field somewhat simpler than Jupiter's. The atmospheres of both planets exhibit belts and zones, alternating bands of light and dark clouds that circle the planets parallel to the equator. These bands are driven by strong winds that can reach hundreds of kilometers per hour. The colors come from trace chemicals and varying cloud compositions at different altitudes. Jupiter's most famous feature is the Great Red Spot, a storm larger than Earth that has been observed continuously since at least the 17th century. The storm rotates counterclockwise and has persisted for centuries, although its size and color change over time. Saturn has its own storms, including periodic planet-wide disturbances known as Great White Spots. These giant storms can alter the planet's appearance for months or years. Saturn also features a distinct hexagonal pattern around its north pole, a persistent jet stream with a six-sided shape that extends deep into the atmosphere. Both Jupiter and Saturn radiate more energy than they receive from the Sun. This excess heat arises from gravitational contraction and, in Saturn's case, the slow separation of helium droplets from hydrogen, releasing heat as they fall deeper. Their cloud layers consist of different materials depending on temperature. Ammonia crystals form the highest clouds. Ammonium hydrosulfide clouds lie below, and deeper layers may contain water clouds. Lightning has been detected on both planets, suggesting energetic weather systems. Jupiter and Saturn are not solitary. They each have extensive systems of moons and rings. Jupiter's known moons number over 80. The four largest, Io, Europa, Ganymede and Callisto, are called the Galilean moons after their discoverer Galileo Galilei. Io is the most volcanically active body in the solar system. Its surface is covered with sulfur and lava lakes, heated by tidal forces as it is squeezed by Jupiter's gravity and interactions with Europa and Ganymede. Europa is slightly smaller than Earth's moon and has a smooth, icy surface crisscrossed with fractures. Beneath this ice lies a global ocean of liquid water, warmed by tidal heating. This subsurface ocean makes Europa a prime target in the search for extraterrestrial life. Ganymede is the largest moon in the solar system, bigger than the planet Mercury. It has its own magnetic field, and also likely harbors a subsurface ocean. Callisto is heavily cratered and may have a salty ocean deep beneath its surface. Smaller moons like Amalthea and Thebe, along with a faint ring system, complete Jupiter's entourage. Saturn has more than 80 known moons, the largest of which is Titan. Titan is remarkable because it has a dense atmosphere, mainly nitrogen with methane and organic haze. Surface temperatures are extremely cold, around -179 degrees Celsius. Methane acts on Titan like water does on Earth. It condenses to form clouds, rains onto the surface, and collects in lakes and seas. Titan's largest lake, Kraken Mare, is larger than the Great Lakes combined. Beneath Titan's icy crust, a subsurface ocean of water mixed with ammonia likely exists. Another standout moon is Enceladus, a small ice-covered world with geysers that erupt from fractures near its south pole. These plumes contain water, ice particles, salts and organic molecules. They are evidence of a liquid ocean beneath the surface, heated by tidal flexing. The Cassini spacecraft flew through these plumes, sampling their composition. The presence of liquid water, energy and organic compounds make Enceladus another compelling candidate for life. Saturn's ring system is one of the most beautiful sights in the solar system. The rings are made of countless particles of ice and rock, ranging in size from dust grains to large boulders. They orbit Saturn in a thin, flat plane, stretching from about 7,000 kilometers above the cloud tops to over 80,000 kilometers outward. The rings are divided into main components named A, B, C, and so on, separated by gaps such as the Cassini division. These gaps are caused by gravitational resonances with Saturn's moons or by embedded moonlets. Although the rings appear solid from a distance, they are mostly empty space. Their thickness is only about 10 meters to a few tens of meters. The origin of the rings is still debated. They may be remnants of a shattered moon or comet, or leftover material from Saturn's formation. Cassini's observations suggest the rings are younger than the planet, possibly only a few 100 million years old. However they formed, they are constantly being reshaped by collisions, moonlet interactions, and micrometeorite bombardment. Jupiter also has rings, though they are much fainter than Saturn's. Voyager 1 first discovered them in 1979. Jupiter's rings consist mainly of dust ejected from small inner moons. These dust particles are quickly destroyed by micrometeoroid impacts and electromagnetic forces, so the rings must be continually replenished by new impacts. The exploration of Jupiter and Saturn has been a triumph of robotic spaceflight. The Pioneer and Voyager missions flew by in the 1970s, taking the first detailed images and measurements. Galileo orbited Jupiter from 1995 to 2003, dropping a probe into the atmosphere and performing multiple flybys of the Galilean moons. Cassini orbited Saturn from 2004 to 2017, studying the planet, rings and moons in unprecedented detail. It delivered the Huygens probe to Titan's surface in 2005, providing our first view from that alien landscape. The Juno spacecraft arrived at Jupiter in 2016 and continues to measure the planet's gravity, magnetic field and composition, giving insight into its internal structure. Future missions like Europa Clipper and JUICE, Jupiter Icy Moons Explorer, will explore the ocean worlds around Jupiter in the 2030s. Dragonfly, a rotorcraft lander, will fly on Titan in the late 2030s to study its chemistry and search for prebiotic processes. Beyond their own systems, Jupiter and Saturn play a protective role for the inner planets. Their gravity can deflect or capture comets and asteroids, reducing the number of potentially hazardous objects that reach Earth. At the same time, their gravitational perturbations can send smaller bodies inward. They are both sculptors and guardians, shaping the architecture of the solar system. On Jupiter, the interaction between the magnetosphere and Io's volcanic plumes produces a plasma torus and generates intense radio emissions. Charged particles from Io's volcanoes are captured by Jupiter's magnetic field and accelerate along field lines, striking the poles and creating auroras hundreds of times more energetic than those on Earth. The currents induced in Io by Jupiter's magnetic field also heat its interior, driving further volcanism. This feedback loop makes the Jupiter-Io interaction one of the most extreme electromagnetic environments in the solar system. Saturn's moons also interact with its magnetosphere. Enceladus, through its plumes, supplies water vapor that becomes ionized and fills a torus around Saturn. This plasma influences the planet's magnetospheric dynamics. The interaction between the magnetic field and these ions affects the rotation rate measured by spacecraft because the charged particles can drag magnetic field lines. Scientists discovered that the apparent length of a Saturn day varied over time. Now they understand that variations in the plasma environment were responsible. Understanding the internal structures of Jupiter and Saturn remains an active area of research. Juno's gravity measurements indicate that Jupiter may have a more diffuse core than previously thought, perhaps extending out to nearly half the planet's radius. This core may be a fuzzy mixture of rock and metal, gradually mixed with hydrogen. Saturn's internal structure is also complex. Models suggest a small rocky core surrounded by a thick layer of metallic hydrogen, overlaid by molecular hydrogen. The presence of helium rain, droplets of helium separating from hydrogen and falling towards the center, is thought to explain the planet's heat and some gravitational anomalies. In many ways, Jupiter and Saturn serve as analogues for the hundreds of gas giants discovered around other stars. Some exoplanets are hot Jupiters orbiting very close to their stars, while others are super Jupiters, much more massive. By studying Jupiter and Saturn up close, we gain insights into how gas giants form, migrate, and affect their planetary systems. The storms, rings, and moons of our giants provide natural laboratories for physics and chemistry under extreme conditions. Through them we learn not only about our own planetary system, but also about the many giant planets discovered around other stars. Beyond Saturn lie two planets that, while similar in size and composition to each other, differ markedly from the gas giants. Uranus and Neptune are called ice giants. This term refers not to surface ice, they have no solid surface, but to the composition of their interiors, which contain a greater proportion of volatile substances like water, ammonia, and methane than do Jupiter and Saturn. These volatiles are referred to as ices in planetary science because they were solids in the cold outer protoplanetary disk. Uranus and Neptune thus offer a different window into planetary diversity. Uranus orbits the Sun at an average distance of about 2.9 billion kilometers, taking 84 Earth years to complete one orbit. It is unique among planets because its axis of rotation is tilted by about 98 degrees. This means Uranus essentially rolls on its side as it orbits the Sun. The cause of this extreme tilt is likely a giant collision early in its history, perhaps with an Earth-sized body. As a result of the tilt, each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. When Voyager 2 flew by Uranus in 1986, the planet appeared almost featureless in visible light, a pale greenish-blue disk, with the Sun shining on its south pole. The lack of visible features suggested a calm atmosphere. More recent observations, especially in infrared, reveal dynamic weather with bright clouds and storms. Winds on Uranus can exceed 900 kilometers per hour. The planet radiates little internal heat, emitting roughly the same energy it receives from the Sun. The atmosphere is mainly hydrogen and helium, with a few percent methane. Methane absorbs red light, giving the blue-green color. Uranus is surrounded by faint, dark rings and at least 27 known moons. Narrow rings are composed mostly of large particles and are shepherded by small moons that keep the ring material confined. The major moons include Titania, Oberon, Umbriel, Ariel, and Miranda. Miranda is especially unusual, with a patchwork of ridges, cliffs, and valleys that hints at a geologically active past. Some Uranian moons may even harbor subsurface oceans, but the system remains largely unexplored since Voyager 2. Neptune, the eighth planet, orbits about 4.5 billion kilometers from the Sun and takes 165 Earth years to complete a revolution. Its existence was predicted by perturbations in Uranus's orbit before telescopic discovery in 1846. Like Uranus, Neptune is rich in water, ammonia, and methane, but its atmosphere appears a deeper blue due to methane and additional still unknown factors. Neptune radiates more than twice the energy it receives from the Sun, driving powerful weather. Winds can exceed 2,000 kilometers per hour, and storms like the Great Dark Spot appear and fade over time. Neptune has faint rings and 14 known moons. Its largest, Triton, orbits in a retrograde direction, suggesting it was captured from the Kuiper belt. Triton has a thin atmosphere and active nitrogen geysers. Its surface shows smooth plains, ridges, and frozen lakes, and it may conceal a subsurface ocean. Neptune's rings include clumpy arcs maintained by the gravity of nearby moons, such as Galatea. Forming Uranus and Neptune so far from the Sun is challenging because material was sparse in the outer disk. Some models propose they formed closer to Jupiter and Saturn and then migrated outward through gravitational interactions. This outward migration helps explain features of the Kuiper belt and small body populations. Understanding ice giant origins informs our view of exoplanets, where mini-Neptunes are common. Beyond Neptune lies the Kuiper belt, a broad donut-shaped region from about 30 to 50 astronomical units containing countless icy bodies. Pluto, about 2,370 kilometers across, orbits every 248 years on a tilted elliptical path. New Horizons revealed smooth nitrogen ice plains, water ice mountains, hazes and vast glaciers, including the heart-shaped Tombor Regio. Pluto's large moon Charon forms a double dwarf planet system with Pluto. Other notable Kuiper belt objects include Eris, slightly smaller than Pluto but more massive, Haumea, an elongated fast rotator with rings, and Makemake, bright with methane ice. KBOs contain ices of water, methane and nitrogen, and are frigid at around -220 degrees Celsius. Collisions and Neptune's gravity scatter some inward as comets. Beyond the Kuiper belt lies the scattered disk, and farther still, the spherical Oort cloud, a reservoir of trillions of distant icy bodies that send long-period comets into the inner solar system when disturbed. Uranus's rings were discovered in 1977 during a stellar occultation when a background star dimmed before and after the planet passed. Voyager 2 later imaged dark, narrow rings with faint dust bands and bright ringlets confined by tiny moons. Neptune's rings were first detected as arcs from Earth. Voyager 2 confirmed incomplete rings composed of clumps maintained by nearby moons like Galatea. The magnetic fields of Uranus and Neptune are strongly tilted and offset from their centers, unlike those of Earth, Jupiter, or Saturn. They likely arise from convecting layers of ionic water-ammonia oceans around the cores. The resulting magnetospheres twist and wobble as the planets rotate, interacting with the solar wind to produce unusual auroras and radiation belts. Studying the ice giants helps interpret the many sub-Neptunes discovered around other stars. Their atmospheres and moons may offer clues to habitability, including possible subsurface oceans on Triton and other distant worlds. The Kuiper belt records planetary migration, with resonant families and distant objects that even hint at a possible unseen Planet 9. Exploration has been limited. Voyager 2 remains our only visitor, while New Horizons revealed Arakoth, a contact binary preserving primordial structure. As we venture farther, Uranus, Neptune, and the Kuiper belt continue to expand our understanding of how planetary systems form and evolve. In our journey through the solar system, a recurring theme is the presence of water. On Earth, liquid water is essential for all known life. It serves as a solvent, a medium for chemical reactions, and a participant in metabolism. For an environment to be habitable by Earth-like life, it must have liquid water, an energy source, and a suite of organic molecules. Although the surface of most bodies in our solar system is dry or frozen, several worlds hide oceans beneath their crusts or host liquids of other kinds on their surfaces. These are the ocean worlds, and they are at the forefront of the search for life beyond Earth. The best-known ocean world is Europa, one of Jupiter's Galilean moons. Its surface is a shell of water ice streaked with dark, linear cracks, evidence of powerful tidal flexing by Jupiter and neighboring moons. This flexing generates heat, maintaining a global ocean tens of kilometers deep beneath the ice. Plumes of water vapor near Europa's south pole hint that the ocean communicates with the surface, lofting material into space where spacecraft can sample it. NASA's Europa Clipper and ESA's JUICE will probe the ice thickness, ocean chemistry and interior structure with repeated flybys. If Europa's ocean contacts a rocky mantle, hydrothermal vents could provide chemical energy. On Earth, such vents teem with life in total darkness. raising the possibility of microbial ecosystems below Europa's ice. Another intriguing ocean world is Ganymede, the largest moon in the solar system. It is the only moon with its own magnetic field, producing shifting auroras that betray a deep, salty, conductive ocean layered beneath ice. JUICE will orbit Ganymede, mapping its magnetosphere, gravity and topography to refine models of its stacked ice-ocean layers and interior. Saturn's moon Enceladus erupts through South Polar tiger stripes, jets of water vapor and ice. Cassini flew through these plumes, detecting salts, silica, hydrogen, and complex organics that point to warm water interacting with rock at the seafloor. The chemistry implies hydrothermal vents and available energy, key ingredients for life. Enceladus is thus among the most promising places to search for biosignatures in the near term. Titan presents a different kind of ocean world. On the surface, liquid methane and ethane fill lakes and seas beneath a dense orange atmosphere. Below the ice crust, a water-ammonia ocean likely persists. The Huygens probe revealed a frigid world shaped by liquid hydrocarbons. NASA's Dragonfly rotorcraft will hop across Titan in the 2030s to study organic chemistry and prebiotic processes. Other candidates include Callisto and Dione, Neptune's captured moon Triton, dwarf planet Ceres with possible brines, and select Kuiper belt objects, each expanding where liquid interiors might exist. Habitability rests on three pillars: liquid water, energy sources, and organic chemistry. Ocean worlds can supply all three: water as solvent, rock-water reactions for energy, and complex carbon molecules as building blocks. Detecting life requires careful interpretation. Instruments like mass spectrometers search for distinctive organics and isotope patterns, while we assess gases such as methane alongside geological context to avoid false positives. Insights from our ocean worlds inform exoplanet studies. Telescopes analyze starlight filtering through alien atmospheres to retrieve spectra, searching for water vapor and other potential biosignature gases. Beyond chemistry and physics lie deeper questions. Could life thrive without sunlight, powered only by chemistry? Would it use molecules unlike our DNA and RNA? How complex could ecosystems become in hidden seas? Our exploration is just beginning. Europa Clipper, JUICE, and Dragonfly will transform what we know, while future plume samplers and ice-penetrating missions push the frontier. In seeking other oceans, we also learn how life began on our own world. Ocean worlds remind us that water is a cosmic sculptor, and perhaps a common cradle. Hidden beneath ice and haze may lie answers to one of humanity's oldest questions: are we alone? We've traveled from the sun's fiery birth through rocky worlds and giant rings, all the way out to icy objects at the edge of the Kuiper belt. We've peeked at tiny asteroids, icy comets and moons with hidden seas that might harbor life. If you've made it this far, thank you for joining me on this voyage. Which part of the solar system's story sparked your imagination? Tell me in the comments, I read them all. Here at the Physics and Cosmos Academy, we don't stop at our own backyard. We dive into the hottest topics in space physics, astrophysics, and cosmology, from the amazing hearts of exploded stars we call neutron stars, to the warped gravity wells of black holes, to the mysteries of dark matter and dark energy, and the instruments we use to study them, from giant ground-based observatories to cutting-edge space telescopes. If that sounds exciting, please tap like and subscribe. Your support helps us keep making calm, thoughtful science stories. Share this space documentary with someone who loves gentle explorations of big ideas like you. Until our next adventure, stay curious, keep looking up, and let's keep exploring the universe together.